Hello and welcome to another video. This unit is an ex-military aircraft VHF transceiver from the period of about the Cold War, I guess 1950s to about 1960 it was made, probably taken out of service in the 1980s. This one is a military version of the standard telephone and cables TR9X or SR9X, something like that, I can't remember. They were given their own military numbers. This one is a TR1998 and there was others available, slightly different bands, but generally in the region of 100 megs up to 145 or 156. This I think was one of the later versions that covered the whole of 100 megs up to 156 megs. It's crystal controlled, crystals are actually held in here, and it's all mechanical tuning on the transmitter and receiver. I'll show you those in a second. It's powered from the 27 volts that would be on the aircraft, and it's got a rotary transformer or a motor generator, whatever you like to call them things, that provides HT, grid bias, and from the supply a regulator to give voltages for the heaters. It weighs quite a bit. It's about 26 pounds in weight as it stands. It's 4-stir cooled. Around the back here we have air filters section. Air goes in here and is forced out on this side. We have, come on, try and get this off in one piece. Air filters, so the air goes in there and out that way. The thing that drives it, if we take off the bottom one, tilt it up. Is a rotary converter here. So that takes 24 volts, 27 volts input and provides a HT and a grid bias circuit. Quite a compact little unit. There are 2, 4, 6, 8, 10, 12, 14, 15, 16, 18, 20, 21 valves in total. So quite a power hungry little thing. A few novelties. If I turn it up like this, we have various things, and I've got some units out of a chassis so I can show you those in a minute. This section is the receiver section. Receiver starts here, that goes off to an IF stage. The IF is at 9.72 megs, quite an unusual frequency, nothing standard. And then the demodulated AM from this goes into an audio amplifier that puts it out to headphones for the rest of the aircraft. On the transmit side, again using the same two valves here to provide part of the multiply stage, that is mixed with some crystal here, which adds the 9.72 megs to it and then gives a final frequency via these two. This would provide about 5 watts output if you're lucky, I guess, 4 to 5 watts output of AM. The modulator stage, microphone audio would come in from the front panel, this transformer through an interstage transformer to the final one, which is the modulation transformer, driven by 2 valves in push-pull here, would actually amplitude modulate the HT and screen voltages to the final valve and the screen to this driver valve here. I'll show you some of the other parts. That's actually, the actual individual parts now. Okay, the first thing I'm going to discuss is this. This is what's actually described on in the unit as a rotary transformer. This takes 27 volts input and changes it to the HT. Here's a quick summary of the circuit. Hopefully you can see that alright. It takes in the nominal 26 to 27 volts LT supply through a few filters, which is basically just caps and inductors, drives it as a motor, and then has two other sections which generate a higher voltage. One of them generates 250 volts, that's fused and goes out through yet another inductor capacitor filter, and grid bias, which will be minus 50 volts here through another fuse, and again another inductor and capacitance output. So it takes 27 volts in, gives you plus 250 and minus 50 volts as well. It has another little unit on it, which is a clutch, which takes itself from the 27 volts, goes out through, and then if shorted to ground, actuates the channel change, and that is this section on the side drives the channel change. So here we have the 26 volt side on this side, so this is the motor side, and with the field coils, when this is actually spun up, will actually generate 250 volts and minus 50 volts from these two sets of contact points on this side. The channel change is a rather neat sort of thing. This obviously spins quite a few thousand RPM, and there's no way the channel change could actually cope with that. So we have this mechanism here. When that pin is grounded, it pulls in a clutch, which is basically this relay here. And what actually happens then, that allows a pawl on the output shaft to actually move this gear, which is then driving this final gear here. So if I spin this up slowly with a screwdriver, you'll see this move very slowly. I think it's something like 400 to 1 or something stupid like that. It is quite a reduction in drive. So if I press that as though I have actually activated the channel change, and I can spin it. Oops, I don't know how to do this and hold it. Oh, there you go, I can hold it that way. With a bit of luck, if I spin this, you might be able to see that gear is moving very slowly, and that would then drive off onto the back of this cog, which would turn around the channel change on this side. So these wafers, if you want to call them that, drive in slides which position tuning cams on here. These would be locked in to the different frequencies. So if you wanted channel 1, that would go out to position and would move the two receiver and transmitter tuning dials to be whatever frequency they actually need to be tuned into. That one is about 135 megs. Go to channel 2, that's somewhere between 125, 135. Channel 3 is about 145, etc. And as you sort of see, each slide pops out when it's on that channel, corresponds to one of the crystal channels in the radio. These are the crystal positions: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 across the bottom. Because this one covers quite a wide range, 100 to 156 megs, you also had little screws here, which initially I thought were trimming caps to actually set the frequency, but they're not. There is also a relay output, or a switched output from this section, which determines a drive output, so you can actually switch one of two different antennas to cover the band that you're actually interested in. So possibly if say frequencies channel positions 1 to 5 are in the low end of the scale, you might have one antenna for that, and 6 to 10 might be on the upper end of the scale, so you might have a different frequency antenna for that one. So it's all mechanically tuned. Let's see, these have got locking cams on this depending on each of these slides that pull out, and they would position a variable, I don't know if you can see that move, a variable capacitor on the transmitter, and I don't know how well you're seeing this on the receiver side. So these shafts here drive receiver tuning and transmitter tuning, which goes to 1, 2, 3, 4, 5 positions, 1, 2, 3, 4, 5 positions on either the receiver or the transmitter to tune the unit up. So you would physically set the cams in these to each frequency. Mechanical tuning before the days of wideband transistors and all the rest of it. On the receiver here we have, on this particular one, front end starts here, so it's front end, amplifier, little block diagram I think I've got, yep, block diagram. This one is the first valve, which is 3V5 RF amplifier. Then this one here is a frequency changer. So RF would come in via this connector, get amplified, go into another valve which would change it down to an IF. Connected on here would be a crystal, one of the 10 position crystals. This would be the oscillator and ×3 multiplier, another ×3 multiplier, and then finally a doubler. That would give an output of 18 times the original crystal frequency. This would connect to the IF stage, and then that would go into the IF amplifier. 9.72 megs would go in here. Amplifier, 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 detector valve. What we'd have then would be a squelch gate, mute type control, a noise limiter, and an audio output valve. This would be the level of audio output into the modulator. There is information on the VMARS website pertaining to the commercial version of these radios, which was made by Standard Telephone and Cables, and it's the TR9X series of radio. That's what it is, it's based on that one. So if you want to get more information you can do. On the transmit side, slightly different. We have the same oscillator valves on the receiver, so a crystal is here, multiplier and a multiplier, and then there is a cross link down in there you can't quite see. We'll take the crystal frequency times 9 and put it into a balance mixer here. There is a 4.86 megs crystal here with its oscillator valve, and what that actually does is that then injects that into the balance mixer with the ×9 here, and then it multiplies it, doubles it up, so it multiplies it by another 2 to actually give you the final frequency output. I know it's as clear as mud, I do apologise for that, but again, I'll try and come off this one. So from the crystals on the receiver front end, ×3 injected into a balance mixer, 4.86 megs stuck in that one. That gives you an output frequency here which is 4.86 plus whatever frequency is coming out here. Then we have a doubler that doubles it, that gets it up to the final frequency of where there's an amplifier and a final power amplifier out to the antenna. So the final frequency is the crystal times 18 plus twice the auxiliary crystal frequency, which is twice times 4.86, or the 9.72 megs, which is the IF frequency. So one crystal would do both the receiver and the transmitter. All the valves are basically 6.3 volts, even the output stages. Most of these are the BG7 type valves. These are CV4014s. There's all sorts of things. The commercial equivalents of these type of valves would be EF91s, EF92s, EL90s, EC90s and EB91s. So quite a lot of the 7-pin valves are used in it. As I say, apart from those two, every other valve is a 7-pin. That's a CV4015, that would be an EF92 I believe. I think this 4014 would be an EF91. Let me have a quick look here. This one I think is a double diode 4025, that would be an EB91, double diode for detectors and AGC. Which, I'll be quite honest, is why I pick up these type of things, basically for the valves. The last stage I've not shown you is this one, and it's not really measured on here, but this is the modulator stage. We have an input valve, would be here, a stage of amplification, and via that transformer, that would be an intervalve transformer which would drive it, shall we say, from single-ended to push-pull, and then a push-pull output stage. This would carry the HT for the, let me get it over there, can you see it? That would give me the HT for the output valve and the driver, and the AM would be put onto the HT driving those two valves, and that would provide hopefully up to about 90-100% modulation if required for the AM output stage. So it's capable of driving about, say, 4 or 5 watts of AM. This one is in particular bad stage, you can see it's corroded, which makes it a little bit hazardous because all the chrome is flaking off and peeling off. So got to be careful with that one. What I'll try and do next is power it up and show you the channel change in operation. Then I'll put it in a box to try and keep the noise down because it is very noisy, and just prove that it does transmit and it does receive, although not that good nowadays. There's lots of components probably need changing, the capacitors and stuff like that, to bring it up to spec, which is probably not something I'll be doing, but basically using it to break it all down, to use it for parts, to get the valves and other various bits and pieces. Right, I shall try and get a power supply down and get it powered up and show you various bits and pieces, show you the channel change, and then connect it to a test set and show you a bit of power output, some mod and some receive audio. Okay, please hold on.